So my name is Laurent Huberdeau, and I'm here to talk about pnut, C transpiler targeting human-readable POSIX shell code. So this is work I'm doing with Cassandre, Hamel, Marc, Feeley, and Stefan Monnier from Université de Montréal. So first we'll see what pnut is, then quickly go over some of our motivations, then some of the implementation and its challenges, and see how it works. So this is pnut in one slide. So on the left, we see perfectly valid C code, and pnut takes that and generates corresponding POSIX shell code. And then we can see that the put s function here takes a string pointer and iterates on it and emits each byte to standard out. And on the right, the shell code has the same structure, so the function name is the same, the local variables names are also the same. The while is compiled to a while loop, put car to a put car call, and so on. And so this is what we mean by human-readable POSIX shell. And so a valid question to ask is why. Like generally, when you use C, you want performance, you want to be close to the hardware, and POSIX shell offers none of that. But there's one very specific use case where it's relevant, and it's for reproducible builds and bootstrapping. So we care about bootstrapping GCC. And there's this famous lecture from Ken Thompson where he described a compiler that was malicious, and the compiler would detect when it was compiling another compiler and inject its malicious code into the resulting binary. And the point that Ken Thompson was trying to make is that detecting such an attack would be very difficult because the compiler binary is opaque. It may be multiple megabytes of machine code. So really there's it would require a lot of work to detect that. And so in our case for GCC, if we want to compile it, we cannot just use any version we have on our machine because that version, we don't necessarily trust it. It may have some malicious code hidden in it. And so if we try to escape the malicious code of our version of GCC by recompiling it, the resulting binary would not be better. And so we're not the first people to attack this problem. There are a stack of projects that try to reduce the size of the binaries required to bootstrap GCC as much as possible. And of course, you always have to trust the layer under you. So you have to trust the hardware, and then you have to trust the operating system, and then all the compilers that lead you to GCC. And so there's a very minimal operating system that's about 4 kilobytes of machine code. That can be used to run a very minimal assembler called hex0 that's only 190 bytes. So in principle, these two blobs could be audited in a reasonable amount of time. And then these can be used to build up an abstraction until the MES-CC compiler is reached that's able to compile TCC and GCC. TCC is the tiny C compiler. It's about 10,000 lines of code, and it's able to compile an old version of GCC. And so once you've reached TCC, which is a reasonably easy target, then you can reach GCC. And then what's special about POSIX shell for it to be useful for bootstrapping? So really it's two things. The first is that it has many different implementations, and it's available on almost any platform. So for example, almost everyone surely knows the bash implementation, but there are others like Corn shell, Ash, Dash, Z shell, and more. And they are so old that they were probably developed independently, and it also shows that it's a very stable platform, which means that it's the ideal candidate for double diverse compilation, which is a technique with a fancy name that's basically just using different compilers that you don't necessarily trust, doing the full bootstrap with them, and then if you get the same executable at the end, then it tells you something about the two compilers you used at the beginning, either that they are compromised in the same way, or more likely that they are uncompromised. And then because POSIX shell is relatively high level, it should be easy to read the code and see what it does. And so our plan is to have two compilers. The first one is pnut shell. So it takes a certain subset of C and turns it into human-readable POSIX shell code. And then obviously, because GCC and TCC use certain constructs of C that cannot really be mapped to POSIX shell, we have a second compiler called pnut.exe that supports this larger subset of C and sends it to binary code. And so we can see that pnut bridges the gap from the shell to GCC, which represents a world where, like, once you have GCC, you can compile basically everything. So here we can see how we would use such compilers to get to GCC. So they're both developed in C. So first, we need to compile pnut shell using an existing C compiler. Here we use GCC. And so we get an executable version of pnut shell. And then we can recompile pnut shell and get a shell script version of it. So now at this point, we require the use of a POSIX shell implementation to run our script. And then we can continue and compile pnut.exe. And then from pnut.exe, we still need to have a shell, and it can be quite slow and limiting, and we want to use the shell as less as possible. And so we can recompile pnut.exe to finally escape the shell and get a binary version of the pnut.exe compiler. And then it's just a matter of compiling TCC and GCC, and we've won. Not quite. So if we look at this diagram, there are a few things that are wrong with it. So first, we have to use like a version of GCC that's like precompiled, so we're not able to trust it. But this is fine because there's nothing stopping us from reading the pnut shell script and ensuring that it doesn't contain any malicious code. And then we still need to use other existing binaries, the POSIX shells. But then because there are just so many implementations available on almost all platforms, we can easily use many of them and do double iris compilation to make sure that they're not compromised. And then because like auditing the pnut shell script will take some time, we don't want to do that every time we compile. So we only want to do that once. And then all you will need to compile GCC would be a POSIX shell implementation, the pnut shell script, and the source code for the other compilers. So having said that, we still have to compile C to POSIX shell. And there are a few challenges ahead. So there's 3 big challenges. The first one is that POSIX shell doesn't offer arrays or data structures. All you have are strings, and you don't have ways of indexing into strings. So we'll have to work around that, especially to implement the heap. And then the shell functions are not able to return values or have local variables. So that's another thing we'll have to take care of. And then in C, I/O is done generally on a character per character basis. And in shell, it's much more line-based. So we'll have to convert from one to the other. So and on top of that, we also have other design goals. We want to be human-readable. So we have to preserve the structure of the C source code as much as possible. Not use eval, because whenever you encounter eval, you could execute arbitrary code, and that would make auditing very difficult. And verifying constants and magic numbers would be very tedious, so we want to avoid them. And because we want to reduce the amount of pre-built binaries we have to trust as much as possible, we don't want to use any external utility, so no use of BC for arithmetic or OD for reading files, and be sufficiently fast for bootstrapping. So POSIX shell has one feature that really saves us, and it's arithmetic expansions. So generally, it's just to evaluate signed integer expressions. So if we wanted to evaluate 5 times 10, we would wrap that in the $parentheses syntax, and it would expand to 50. And it can also refer to variables. So those are environment variables. So you can refer to, for example, a plus, and add it to 10. And fortunately, POSIX shell supports all of the C arithmetic and logical operators. So this is very convenient, especially for assignments. So we can assign to new variables, and even those that were not previously declared. And that means we can assign the memory locations, the environment variables prefixed with underscore, and then the address. So the first memory location will be _1, then _2, and so on. And to index, we can simply nest the arithmetic expansion in a way that constructs variable names dynamically. And so here, for example, if we want to dereference the memory location at address 2, we use 2 arithmetic expansions. So the first one contains x equals underscore, and then we open a second arithmetic expansion that will expand to 2. And so the outer expansion will execute x equals underscore 2, and so read that memory location. Sometimes you want to ignore the result of the expression, so you'll see that syntax in some of the example where it starts with colon, it just ignores the result, but it still evaluates the expression. Generally, this is for assignments. And so bringing back the put s example from the beginning, we can see the while loop condition dereferences s, checks if it's 0, so if it's the null byte, and if it's not the null byte, it will emit it to standard out. And in shell, we can see we have 2 arithmetic expansion to dereference s, and we compare the result to 0. And if it's not 0, then we keep going and call the putCar function, again passing it the value of the byte. So that takes care of the first implementation challenge. And now that we have a heap, we can build data structure, so it helps with the other 2. So we can extend the shell functions and kind of match the C syntax of where you capture the result of a function call. So if you want the result of a function, you can see you write answer equals the function call. And in shell, what we do is every function has as its first argument something we call the return location, and it's just the name of the variable where we want the result to be in. So we can see the meaning of life function. What it does an arithmetic expansion where the left-hand side is $1, and $1 refers to that return location. And so if we want to call the meaning of life function and get its result in the answer variable, we just have to give it as its first argument the answer string. And so we can see it reads almost naturally. So instead of being on the left, the return location appears on the right, but the transformation is very natural, and like there's nothing surprising with it. And then for local variables and parameters, we just use a callee save calling convention. So whenever a function wants to use a variable, it first has to save the value, and then before returning, it has to restore the value of the variable. And we just we give nicer name to these push and pop operations that happen on a stack. So let pushes the value of a variable and initializes it, and then end let does the opposite at the end of a function call and restores the original value. So that can be a little bit slow because for every local variable you have a shell function call. And so fortunately there's an alternative implementation where there's the set command where you can change the parameter of a function dynamically. And so we can use that to add more parameters to the function call and store value that way. This is much faster, but it's much harder to read, and we ended up not having to use this optimization. But it's nice to know that it exists. So that takes care of the second challenge. And then for character-based I/O, Shell has file descriptors, so that's very convenient. And it has 2 built-in. The first one is read, that just reads a line, and then printf that can output any byte. And so with those, we can relatively easily implement the Unix open read and write functions. So we just have to buffer the read calls to read lines and then only feed the characters as they are needed. And that completes the implementation challenges. So we still had other design goals. So let's look at those again. So is it auditable and human readable? So far we've preserved the structure of the C source code. We haven't used eval. Instead, we've used arithmetic expansion as a limited or restricted eval that's still auditable. But we haven't really done anything regarding constants and magic numbers, so we'll have to get to that. We haven't used external utilities for arithmetic or I/O, and we're sufficiently fast for bootstrapping. We'll see later a table with a few times with some benchmarks. And so for avoiding magic numbers in C, really there's 2 sources of magic numbers. The first one are character constants. They don't exist in Shell. And so instead of replacing the value of character constants with their ASCII code, we just define global variables that are read-only to give a name to these ASCII code. So if you refer to the character A, really we'll replace that with a reference to the shell variable underscore underscore A underscore underscore. It kind of looks like quote. And then for structure field offsets, we do the same. So the first field of a structure is at offset 0. The second one is at offset 1. And we do the same thing for the size of the structure. So whenever you access, so to read or to write a C structure, we just refer to that variable. And then another source of constants in C are string literals, and they don't have the same representation in C and in shell, so we have to convert from one to the other. And so we do that using the def string function. And so whenever we encounter a string literal, we add a def string function call before that initializes the string, so unpacks it into memory on the first time it's used. So does it work? Can we actually implement a reasonably large subset of C in POSIX shell? The answer is yes. So this chart shows the C language support that both of our compiler has. So pnut shell supports function declarations, of course, if, switch statements, all the loops, structures, enums. It can do pointer arithmetic. It has dynamic memory allocation, some basic I/O functions, and a C preprocessor. And then pnut.exe extends that with switch, fall through, gotos, the address of operator, stack allocated structures, and so on. And then to compile TCC, there are things we don't yet support. So those are, for example, floats and unsigned numbers, bit fields, function pointers, and variadic functions, but it should be relatively quick to get there. And then more results. So as a rough measure of readability, we can compare the C source code size to the shell source code size, and it's about 35% larger, so not too different. And that includes like hard-coded runtime functions. So in practice, the difference is even smaller. Also, pnut shell can compile existing programs we haven't written. So it's proof that some C programs use the subset we're targeting, and the code we generate can work with a very old version of Bash. So we can use the version 2.05b that comes from 2002. And in terms of bootstrapping time, to compile pnut.exe using the pnut shell script, it takes about a minute, more or less, depending on the shell. There's Z shell that stands out. For some reason, it's much slower, but it is still very reasonable, especially for something that would only happen once. Like, right when you have compiled pnut.exe and TCC and GCC, you no longer have a reason to use pnut shell. And then, so in conclusion, pnut shell is a viable compilation target. We're still working on TCC to eventually be able to compile it from the shell. And if you want to see the code pnut shell generates, we have a live or a web code editor you can use, and it's at the pnut.sh website. Thank you.
We have plenty of time for questions.
So with pipes, shells are very good at parallelism. Can you benefit from that at all?
Not really. Like there's not any like C construct that directly matches that. So we only use redirection operators, but not pipes.
Okay, I was hoping maybe you could turn out to be faster than C if you could pipe things and get them to parallelize in a good way, but maybe
the compiler is really, so it's a one-pass compiler. We try to consume as less memory as possible. So we really want to avoid doing things in parallel, but it could be interesting to see if there are like ways to program or use these shell features in a higher level way using C.
Hi. I was curious. I mean, it's a very interesting tool. I was curious what subset of C can be supported, or rather, the other way around, what subset of C cannot be supported.
So if we come back here, for example, POSIX shell doesn't have gotos. So if we wanted to support that, we would have to use some kind of trampoline mechanism, and then the shell code would no longer be human readable. Like we would no longer have the same structure on both sides. There's no floating point numbers in POSIX shell, so we would have to implement that from scratch, and it's not obvious how we would do that. Yeah, those are two examples.
I mean, I was curious, how do you handle structs, or like say unions, right?
Yeah, unions are kind of like structures. We don't support them at the moment, but like here in this example, like we have dynamic memory allocation because we have a heap, so you can reserve a space in that heap to have like two-layer structure. And so that's how we, like a structure is just like an array where you index with like names at specific locations. And so that's how we implement it. Sorry, what?
Do you have a tool that says, hey, this is a program that cannot be handled?
Well, pnut will tell you. Like at some point it will encounter a construct that it's not able to parse or compile, and then it will just crash. Hopefully with a nice error message.
Any more questions?
So I wonder if you have considered ways to either automate or partially automate or assist in this auditing process.
The what?
To assist in the auditing process.
Like there's always the issue of using tools, because then you have to trust these tools. So we haven't really explored that. Like one way could just be to reduce the amount of code that has to be audited as much as possible. Still, like it's only about, so if we look at the size of the pnut.exe C source code, it's only 5,000 lines of code. 5,000 lines of code. And so like it could be done in a few hours maybe.
Perhaps you can have a decompilation process. You can compile, decompile, and compare.
We do have an option in pnut where we generate the original C source code as a comment, and then we show the resulting shell code. So that helps with the comparison process. But then because we use GCC, and GCC could somehow change that original C source code, it could be misleading to use that for auditing. So really, we're on our own in terms of auditing, just because like we have to be almost paranoid of every tool we use.
Did any other questions pop up? In that case, let's thank our speaker.